All right, so today we're going to be talking about how we need to prepare for Lab 5. In Lab 5, we're going to be performing a titration, just like in Lab 4. Titrations, generally, people think of acid-base reactions, combining an acid with a base and learning about the concentration of either the acid or the base. But titrations can be any kinds of reactions. All we need to have is some sort of an indicator to tell us when the reaction is done, a known reaction. One of our samples, one of our reactants, reagents will be an unknown and the other can be the known. All right, so in this reaction, this is the reaction that we're going to be looking at. Silver ions combining with chloride ions to produce silver chloride, which is a solid. So this is a precipitation reaction. Now, the indicator that we use has a certain color to it, and it will change when all of the chloride ion, or silver ion, is pulled out of solution. So the silver ion interacts with the dye, but when the last amount of silver ion is pulled out of solution, then the silver ion will change. Okay? So, in this procedure, we're going to set up a precipitation titration just like in the previous lab, in Lab 4. We're going to have a burette, right? And we're going to have a place where our titration is going to occur. This is going to be on top of a stir plate, right? We're going to make sure we don't turn on the heater, just like before, okay? And we're going to use a stir bar. The dye, the indicator that we're going to be using is called dichlorofluorescein. All right. We're going to be provided a solution of 1,000 ppm silver ion. All right. Now, when we say 1,000 ppm, we only talked briefly about this before when we were talking about ways to express concentration. But ppm means, so if I have 1,000 parts per million, that means 1,000 milligrams of solute per liter of solution. Okay? Now, the concentrations of these solutes is very, very low. So that's why we can say liters of solution. Really, it's 1,000 milligrams of solute for every million milligrams, and that's why they call it parts per million. But 1 million milligrams, so if I said 1 million milligrams of solution, right? That's the same, because this is water and it has a density of 1 gram per milliliter. That's the same as 1 million milliliters of solution. All right. So, let's see, did I do that right? No, sorry, it's not the same as 1 million milliliters. It's the same as 1 million microliters, because 1 milligram of water weighs 1 microliter of solution. And a million microliters, so 1 million, a million microliters, that mu is how you make the micro, that's equal to 1 liter of solution. Okay? So again, these are still over 1,000 milligrams of solute. So, because the density of these solutions are always going to be close to 1, because when we're expressing things in terms of parts per million, it's because their concentration is relatively low, therefore they're not going to influence the density of the solution significantly. Because that is, again, 1,000 milligrams, the density is 1 gram per milliliter. That makes it 1 million milligrams, 1 million microliters. 1 million microliters, that's 1 liter of solution. So, you can try to understand that, or just always remember, and it's not a good idea to always remember this, but at least for this lab, that parts per million means milligrams solute per liter of solution. Okay? So we're going to be provided a 1,000 parts per million silver ion solution. And initially, we're going to practice titrating 100 milliliter samples of a provided standard of 50 parts per million chloride ion solution. Okay? And the idea here of practicing with 100 milliliter samples of the 50 parts per million solution is to help us see what the color change looks like. Because often in titrations, and this is not an exception in this titration, it's difficult to see the color change that we'll be after. Right? So, we have 1,000 part per million silver ion solution, and that's going to be in our burette. And then we're going to have also provided a 50 part per million chloride ion solution, and we're going to put into our flask 100 milliliters of this solution. 100 milliliters of solution. Okay? You won't have to add water. It wouldn't hurt to add water, but we don't need to for any reason because that will be plenty of volume. Okay? We're going to want to make sure we have a stir bar in there. Right? And then after we get comfortable, now you should be able to know how many milliliters, how many milliliters of the 1,000 parts per million solution it should require to titrate the 100 milliliters of 50 part per million chloride ion solution that we have in here. And you want to do that calculation before you come to class. You want to find out how many milliliters of the 1,000 parts per million solution are required to titrate the 50 part per million solution, the 100 milliliters of the 50 part per million solution. Okay? This calculation is not directly related to this equation, right? This equation up here, silver ions and chloride ions, that's mole ratio, right? 1 mole of silver ion, 1 mole of chloride ion. But this is 1,000 milligrams of silver ion, 50 milligrams of chloride ion per liter, right? 1,000 parts per million, 1,000 milligrams of silver ion per liter of solution, 50 milligrams of chloride ion per solution, or per liter of solution. So you can do a calculation. You will have to go to the land of the moles, right? And then you can use the power of the equation to identify the relative ratio and identify how many milliliters of your 1,000 parts per million solution of silver ion is going to require. So that'll be something you can know, and once you've practiced and become comfortable with that titration, you're going to titrate a sample of tap water by adding 100 milliliters of the tap water into an Erlenmeyer flask with 3 drops of your indicator solution. And you want to make sure you do it 4 times to get a good average and standard deviation. And determine what the concentration of the chloride ion in tap water is. All right? And then after you're done with that, you're going to repeat the process, but you're going to use a sample of ocean water. And the ocean water is much higher in concentration of chloride ion, so we're going to be using only 1/2 milliliter of ocean water with 95 milliliters of deionized water. Okay? And you want to make sure you do that, and you're going to report your answers for the concentration of chloride ion of the tap water, and also the concentration of chloride ion for the ocean water in parts per million. Okay? So the titration is something that you'll get used to. You can practice more than 4 times, as many times as it takes to get used to it, as here in step 4, right? So that's not hard. Kind of getting used to the titration is a little bit of a learning there. and which is good because we need to be able to recognize how to do precipitation titrations. But the hard part here might be dealing with parts per million, figuring out what parts per million means and how that relates to molarity like we're used to. Okay, so maybe we do one concentration, one calculation, and determine the concentration of silver ion, not in parts per million, but in molarity. Okay, so we'll do this one together. So again, what we want here is we want to know the moles of silver ion for every 1 liter of solution. And we're starting with 1,000 parts per million silver ion. I'm going to change that right now to milligrams of silver ion, right, for every 1 liter of solution. So we got liters of solution on bottom. That's good. All we need to do is get our milligrams of silver ion to moles of silver ion, right? So we go milligrams silver, grams of silver ion, grams of silver ion to moles of silver ion. All right? Pretty straightforward. That's going to tell us what the molar concentration of our silver ion is. We could do that same thing for the we want to know the molar concentration of the chloride ion for every liter of solution. Specifically our $50 parts per million, right? We want to, this is the one we're going to practice. So we use find our 50 parts per million. Let's see. Yeah. So we're going to want to find out what the 50 parts per million solution is. 50 milligrams of chloride ion for every 1 liter of solution. Milligrams of chloride to grams of chloride ion. Grams of chloride ion to moles of chloride ion. We know that these react in a 1-to-1 molar ratio, right? That's our reaction. Silver ion plus chloride ion going to silver chloride solid, right? We know that that is how these are going to react. So we just need to find the relative molarities of these two solutions and find out what ratio of volumes should be expected. We know we're going to use 100 milliliters of this. So after we get the moles per liter of chloride ion, we could identify the moles of chloride ion in solution by multiplying by our liters of, which is 0.1 liter of the chloride ion solution. Right, then we could isolate moles of chloride ion. And from the moles of chloride ion, we would know how many moles of silver ion, right? For silver ion, for the silver ion solution concentration, we would want to identify the milliliters of the silver ion solution that are going to be required in our titration, right? And we would know how many moles of chloride ion. We could put that here. Moles of chloride ion that are going to be in the solution, in the sample that we start with. Convert that moles of chloride ion to moles of silver ion. That's a 1-to-1 ratio as per our reaction there, right? Okay, and then we can get moles of silver ion into liters of silver ion by using the molarity, moles of silver ion. So whatever our calculated molarity is up here, moles per liter, and then go liters to milliliters, 1,000 milliliters to liters, to get the milliliters of silver ion necessary to perform this titration, right? Those are our practice titrations. Okay? All right, that's pretty much it. Again, we got a couple of unknowns. A few things to remind you of. First of all, or to tell you about, there's a warning in here, right here, warning, the silver nitrate solution is not particularly harmful, but if it gets on your skin, it will turn a dark black color, and it won't go away for about 4 days, maybe a week. So if you want to avoid that, then make sure you wear protective, personal protective equipment like gloves. All right, and you could use also a lab coat to make sure it doesn't splash on your hands. Goggles obviously are always going to be worn. Remember that you have two unknowns in this lab, so don't forget to run both of them. Sometimes people run one unknown and then they move on, or maybe it's because they don't write it down in their lab book, but a lot of people just end up reporting in their lab report one unknown. Well, we have two. We have the tap water, which is an unknown, and we have also the ocean water, which will be an unknown for us. Okay? And like it says here, we want to repeat or report our answers in parts per million. So if you know the molarity, you can use the opposite of this to go from molarity to parts per million solution. All right, that shouldn't be too hard. The indicator, again, let's talk a little bit about the indicator, how the indicator changes color. The indicator changes color because of the silver ions that will attach to its surface. So initially, the indicator is in the presence of the chloride ion, negative charges, but as the silver ion adds, it will take away those chloride ions, and eventually, when there's excess silver nitrate, those silver ions will begin to, excess amount of silver nitrate will begin to change the color of the dye. So it's those excess silver ions that changes the color of the dye. Okay, so we'll see you next Thursday.